Good morning. Today we are going to see the characteristics of the insulators. In last lecture, we see the metal, then band theory of metal, then any curves and their characteristics, special typical type of any curves. Now we are going to see uh, insulators. Diamond is an insulator, that is non-conductor. Diamond and graphite are the allotropes of carbon. In diamond, carbon atom possesses 4 valence electrons, 2s1, 2p3. It is the electronic configuration of carbon. Due to bonding, both the 2s and 2p bands are completely filled. Moreover, the gap between the filled band and the next higher empty band is very large. As a result, electrons cannot move from filled energy band to empty energy band or level and cannot give rise to conductivity. This is shown in the figure. It is a typical NE curve for an insulator. See there, Mn is the gap which is very large, and electron transfer from filled band to conduction band is not possible. Effect of temperature and impurity on conductivity. Conductivity decreases with increase in resistance. The resistance increases with increase in temperature and the presence of an impurity in the metal. Thus, both increase in temperature and the addition of impurity decreases the electrical conductivity of the metal. First, we see the effect of temperature. We have seen that greater the number of states in the energy band, greater is free movement of the electrons, and hence higher should be the conductivity. Generally, material expands on heating and hence more space is available. Thus, we expect increase in conductivity of the metal with increase in temperature due to passage of electrons into completely filled or vacant energy bands. The usual observation is that conductivity decreases with increase in temperature. This is because heating produces vibration of the atoms. The atomic vibrations increases with increase in temperature, which creates disturbances in the regular arrangement of the atoms in the crystal structure of the metal. That is, lattice becomes irregular. The vibrating atom also creates a vibrating field which scatters the electrons in two different energy states. This scattering of electron decreases the free motion of the electrons and hence decrease the conductivity of the metal. it can be stated that scattering of electrons is proportional to absolute temperature. This effect of temperature on conductivity may also be explained in terms of molecular orbital theory. In a highly regular arrangement of the atoms in the metal crystal, the molecular orbitals are spread completely over all the atoms. The electrons in these molecular orbitals are localized and highly mobile. If irregularities are created in the crystal lattice, then delocalization of electrons decreases. That is, localization of band increases with increase in temperature, which results in the decrease of conductivity of metals. Second, effect of impurity. The regular order of arrangement of the atoms and the regular field in the crystal lattice of a metal is also distributed by the addition of get disturbed by the addition of the small quantity of an impurity. For example, the conductivity of copper metal decreases by the addition of the manganese in it. Thus, Mn atoms disturb the regular arrangement of the copper atom and produce a defect in the crystal structure of copper. Binding energy in metals. We are going to see the binding energies in the metal crystal. Binding energy refers to the strength of a bond or the energy required to break a bond, that is bond energy. We shall mainly compare to the bond energies in metallic crystal with those of covalent compounds. For covalent compounds, the bond energy is the measure of the energy required to split a covalent bond, while for metal the bond energy is the heat of dissociation. It measures of the energy required to break down the binding forces in the metal to produce free atoms. Following points suggest that metallic bond is weaker than a covalent bond. First, the interatomic distance in the metal crystal is greater than in diatomic molecules. Second, in metals, each atom is bonded to 8 to 12 neighboring atoms, and there is a shortage of electrons for bond formation, while covalent bond contains electron pair between the two adjacent atoms. Third, metal content aggregate of atoms, while covalent compounds contain discrete molecules. Though a metallic bond is weaker than a covalent bond, the net strength of the metallic bond is large due to very large number of non-directional bonds. In other words, the weakness of metallic bond is compensated by the presence of a large number of bonds widely spread throughout the crystal lattice. In general, metallic bond is non-directional and weak, whereas covalent bond is directional and strong. This is the reason why the energy required to vaporize a whole molecule of a metal to free the atoms in smaller than the energy required to vaporize a mole of covalent compound, for example graphite.